Welcome to lecture 1.3. And once you finish this and do your book reading and everything else that you have to do, you should be able to distinguish between conductors, insulators, semiconductors, and superconductors, identify what is meant by electrically isolated and by grounding, explain how a charged object can set up an induced charge in a second object. This is the review, not the first time you should be seeing it. Okay, insulators are also called non-conductors. The electrons in an insulator are all tightly bound to the positive nuclei and are not free to move around. Charging an insulator by friction leaves patches of molecular ions on the surface, and we explained that in a previous lecture, but these patches are immobile. They don't move. The insulator elements are usually found on the upper right-hand corner of the periodic table. They're over here because these elements are all highly electronegative and they hold tightly onto their valence electrons. So the electrons are tightly bound and remain with the particular atoms. In other words, there are no conduction electrons. The electrons are not free to wander around to other atoms in the material. They're poor conductors of electricity and heat. Under the right or wrong circumstances, however, any non-conductor can become a conductor. Now, the myth that rubber-soled shoes protect you from lightning is purely a myth. And the myth that you're safer in a car in a thunderstorm because of the rubber tires, is not because those rubber tires are non-conductors. They are actually made to be conductors for safety reasons, and we'll explain that later in a later lecture, why the rubber tires are not non-conductors. They actually are conductors. Examples of non-conductors include most plastics, pure rubber, glass, ceramics, pure water, and dry air. Notice I said pure rubber. There's a hint on what it is with the tires. Tires have steel metal radials in them, and steel is a good conductor. Now, in metals, the outer atomic electrons, that is the conduction electrons, are only weakly bound to the nuclei. These outer electrons easily become detached from the parent nuclei and are free to wander through the entire solid. They form a partially degenerate electron sea of roving negative charges. The solid as a whole will remain electrically neutral, but the electrons are now like a negatively charged fluid permeating an array of positively charged ion cores. So it's sort of like that weightless, frictionless fluid we talked about during Benjamin Franklin's day. So that actually is a pretty good model. Now, conductors are found on the left side of the periodic table where the electronegativities are low and the atoms do not tightly hold to their valence electrons. Good electrical conductors are also good heat conductors and are usually shiny for the same reasons. Loose electrons that can carry charge and thermal energy and easily interact with and reflect light. Other types of materials that conduct are molten salts, dissolved salts, acids, bases, and plasma. And these non-solid materials, free-moving negative and positive ions, do the conducting. And plasmas are gases that are heated or charged until the outer electrons leave the atoms. In these materials, both the loose electrons and the positive ions move and conduct. Now, in power lines, the charge moves much more easily through the hundreds of kilometers of metal wire than it does through the few centimeters of insulating material that separates the wire from the supporting tower. A substance classified as a conductor and insulator is done so based on how tightly the atoms of the substance hold their electrons. The conductivity of metal can be more than 1,000,000,000,000 times greater than the conductivity of insulators such as glass. Now, semiconductors, as you probably guessed from the name, are something between conductors and non-conductors. They are materials that can be made to behave sometimes as insulators and sometimes as conductors. They're often doped with other materials to give them specific electrical properties. The atoms in a semiconductor hold their electrons until they're given a small energy boost. Then they can flow freely, but usually in only one direction. This occurs in things like photovoltaic cells that convert solar energy light into electrical energy, and in LED light-emitting diodes that can convert electrical energy directly into light. So these basically are the same beast, just run in reverse. Thin layers of semiconductor materials sandwiched together make up transistors. These are used in every electronic device that you have. Your phone, your TV, your computer, all of these use transistors. Semiconductor elements are carbon, silicon, sulfur, germanium, tin, selenium, tellurium, and these are logically enough sandwiched between the metals and non-metals in the periodic table. So here they are. Okay, here are the metals, here are the non-metals, and these purple ones in here right between the metals and non-metals are the semiconductors. Okay, now there's another class called a superconductor. Conductors have a small resistance to flow of electric charge. Semiconductors have a moderate and often variable or directional resistance to the flow of electric charge. Insulators have a great resistance to flow of electrical charge. Superconductors, on the other hand, are certain materials where the electrical resistance disappears under certain conditions. The electrons can then move easily through the material with no friction and no wasteful heating. Now, this would be a huge boon for industry because of the savings in energy costs, no more waste due to heating. Unfortunately, this only occurs for very low temperatures, close to 0 Kelvin. So that means you got to pay the price for refrigeration, but they'd be great in space. And they are typically require exotic, expensive materials that are hard to machine and handle. The search is on for room temperature superconductors that are inexpensive and easy to handle. Unfortunately, you never get something for nothing. Okay, now one of the many ways that electric charge can be transferred is by friction. And we've experienced this, especially in wintertime when the air gets dry. We can stroke a cat's fur and we can see and hear the crackle sparks that are produced. We can comb our hair in front of a mirror in a dark room and see and hear the sparks of electricity. We can scuff our shoes across the rug and feel the tingles we reach for the doorknob. This happens in the dryer when clothing rubs on the dryer drum and results in that annoying static cling that sticks your socks together. What's going on here is electrons are being transferred by friction when one material rubs electrons from another material. Now, conductors can be charged by contact with a charged plastic object. So we have a plastic object here, we bring it near a conductor. When a charged object is placed in contact with a neutral conductor, some of the charge will quickly, almost at the speed of light, transfer to the material to the neutral conductor. The electrons in the conductor, of course, are free to move because that's what a conductor is. They repel each other. They try to get as far away from each other as possible because they all are like charges, are all negative. Once the charge gets transferred to the metal, the repulsive forces between the electrons cause them to swiftly move as far apart as possible from each other. They spread themselves over the surface of the conductor and they concentrate at any sharp points on the conductor. Now, later in the course, we'll explain why that is. Now, when we touch the charged metal surface with a finger, the charges that repel each other now have a new conducting path to a larger reservoir for electric charge, and that's us. Now, humans can be good or poor conductors depending on conditions, like how damp your skin is. Damp skin is covered with salt water, a good conductor. Bodily fluids and tissues also are largely salt water. Nerves are also conductors. They work by electrochemical conduction of electrical impulses. So in other words, you're basically an electrical machine. Depending on the conditions, you can be a very good conductor. So what happens here, if you touch a charged object like a metal here, you suddenly become an additional path and source, okay, and sink, a larger reservoir for electric charge. And then you get a shock. Any excess charge that is initially confined in the metal can now spread over the larger metal plus superconductor, and you get a shock as the charge flows. Now, a charged object held close to a metal electroscope will cause the leaves to repel each other. So what goes on here is you end up with, you bring in a charged object, this happens to be positively charged, that will attract the electrons, which are free to move in the metal, and they will all gather up, or at least most of them will gather up at the top here. That leaves these positive ions down at the bottom, and that causes these leaves, which are free to move, to repel each other, so it makes them spread out. So how do charged objects of either sign actually exert an attractive force on a neutral object? Okay, well, here's an initially neutral object. You bring a charged object close to it. Now, the metal as a whole is still electrically neutral. No charges have been removed or added to the object as a whole. But because this is positive here, it will attract the free to move negative charges in the metal to the top here and leave the ions, the positive ions, at the bottom. And this is what we call polarization. The object has been polarized. It has suffered a charge separation caused by the proximity of this charged object. Charge polarization is the separation of positive and negative charges in a neutral object, usually due to some sort of proximity of another charged object. Because the electric force decreases with distance. Okay, and remember, it's an inverse square law. The attractive forces on the electrons at the top is greater than the repulsive forces on the ions at the bottom. So the net force is toward the charged object. So in other words, a charged object will attract a neutral object. Now, what happens when you remove the charged object? Well, the minute you remove it, these charges redistribute themselves, the forces all disappear. Now, an electroscope, when you remove this, as soon as this goes away, these electrons are free to move. They don't want to stay here. They're going to redistribute themselves over the entire object. And it's because this is a good conductor. The electron C quickly reflows and readjusts. Once you remove the charged object, the leaves fall back together, the excess charge departs and distributes itself over the entire object. Doesn't leave the object, just redistributes. Any forces of attraction go to zero. Now, charge polarization can also be induced and occur in insulators that are near a charged object. When a charged object is brought near an insulator, there are no free electrons to migrate through the insulating material. Instead, there is a rearrangement of the positions of charges within the atoms and molecules themselves. You can sort of see here's the negatively charged object, and it's going to slightly distort all these molecules inside of here, all these atoms and molecules. And the positive charges will end up sort of being pulled slightly closer to this negative charge. Negative ones are going to be slightly pushed away. And remember, it's an inverse square law, so close wins. So what happens here? We've got two atoms. Here's when nothing is nearby this atom. So it's just basically, it's symmetrical. Okay, there isn't any charge separation or anything else like this. But you bring some charge near it. In this case, we either brought a negative charge to this side or a positive charge to that side. So in this case, we're just going to assume the negative charge is brought to the left side. So one side of the atom or molecule is induced to be slightly more positive or negative than the opposite side, which will assume the opposite and equal amount of charge. In other words, it's just a charge separation, otherwise known as charge polarization. The atom or molecule is then said to be electrically polarized. So what happens is when a negative external charge is brought closer from the left, the charges within the neutral atom or molecule will rearrange themselves slightly. It doesn't take much. Now, all the atoms or molecules near the surface of the insulator become electrically polarized. They become temporary or induced dipoles, and we'll explain later what that is. As soon as the external charge is removed, the induced polarization disappears as the charges go back to the normal configuration. But while this is near here, there's an attractive force between the charged object and the other object. And that's due to the fact that the closeness wins here, because it's an inverse square law. So polarization explains why electrically neutral bits of paper are attracted to a charged object such as a charged cone. The molecules in the paper are polarized, with the oppositely charged sides of the molecules closest to the charged object. So in other words, you bring a negatively charged cone near a piece of paper, the side of the paper that's closest to the cone becomes positively charged. The other side becomes negatively charged, but close wins, so it becomes attracted. Since the opposites are closer to each other than the likes, and the opposites attract to paper, the paper gets attracted to the cone because it's an inverse square law and close wins. Now, this can happen when you do this famous trick with a balloon. You know, you rub an inflated balloon on your hair, it becomes negatively charged. You place the balloon against the wall and it sticks. So what's going on in here is the charge on the balloon polarizes the charges in the wall, okay, and induces an opposite surface charge on the wall. The charge on the balloon is slightly closer to the opposite induced charge than the charge on the same side, so close wins and attraction wins. So this means that the balloon will stick to the wall. The charges are not able to leave the material, so they don't neutralize each other easily, and the balloon stays stuck to the wall. Now, many molecules like water, for example, are electrically polarized in their normal state. We were talking about here, these are atoms or molecules that are not normally polarized. Here we have natural or permanent electric dipoles. Now, the distribution of electric charge is not perfectly symmetrical in these molecules, and you can see that here. Oxygen is highly electronegative. It steals the electrons away from the two hydrogen here, so it winds up with a positive charge on this side and a negative charge on that side, and that's permanent. It doesn't go away. So there's more negative charge on one side of the molecule than the other. These molecules are called electric dipoles, and they're all actually called natural or permanent electric dipoles because they don't disappear. This lets us cook food and boil water in a microwave oven and leads to relatively strong intermolecular forces between the positive and negative ends of adjacent molecules, which explains many of water's unique and vital properties. And we'll explain later how this works in microwave ovens. But at any rate, if you picture other water molecules here, the positive hydrogens of those other water molecules are going to be more strongly attracted to this negative oxygen here. So they have a tendency to form very weak bonds here. But those bonds, despite the fact of being relatively weak, they cause unique properties for water. Water is high specific and high latent heat, which is why we use it as a cooling fluid. Water is high surface tension. Water is high boiling temperature. The fact that snowflakes are six-sided and ice floats on water. And we're not going to go into details with that. If you're interested in that, I'll be happy to explain it to you after class. The figure below shows how a neutral atom is polarized by an external charge, forming an induced electric dipole. You bring an external charge near a neutral atom, and the external charge will tug on the various parts of the atom. In this case, because it's positive, it's going to tug on the electron cloud, pulling the electron cloud closer to the external charge, while simultaneously driving the positively charged nucleus of the atom slightly further away. This separation of charge is called an induced electric dipole. Now, the net effect of this is, as we talked about before, is that there will be a net attractive force toward the external charge due to the difference in forces induced here. Once you remove the external charge, this whole business disappears. The nucleus of the atom ends up centered again inside the electron cloud. and the atom goes back to normal, the forces disappear, the dipole disappears, and everything's back to normal. So when an insulator is brought near an external charge, all the individual atoms inside the insulator become polarized. The polarization force acting on each atom produces a net polarization force toward the external charge, and these in here are called induced dipoles. They only hang around as long as there is an external charge nearby. If the external charge is removed, the effect vanishes and they go back to normal. Now, we mentioned grounding a little bit. Grounding is also called earthing. That's because the Earth is a huge sink or source of electric charge. It has a huge iron core and actually is an electromagnetic generator. And later when we talk about generators, we'll talk about the Earth. When we touch the surface of a charged object with a finger and then connect it to something else that is grounded, such as a water pipe, charges that repel each other have a conducting path to the practically infinite reservoir for both kinds of electric charge, the ground, the Earth itself. When we allow charges to move off of or onto a conductor by touching, that is connecting it to ground, we are grounding it. It is also called earthing it for obvious reasons, because you're connecting it to the ground. Charging by induction can be illustrated using two insulated metal spheres. The uncharged metal spheres are initially touching each other. That means they form a single non-charged conductor. If a charged object is brought near a conducting surface, even without physical contact, the electrons will move in the conducting surface. They're going to try, in this case, we brought a negatively charged object near sphere A. That means the electrons in sphere A are going to run screaming over to sphere B to get as far away from this negatively charged object as possible. Then what we do is we separate the spheres and we remove the charged object. The net result of this is that A ends up positively charged, B ends up negatively charged. And this means that we have charged these spheres by induction, which is inducing the charging of an object through the proximity of another charged object without direct contact between them. Charging by induction and grounding can be illustrated by using a metal sphere hanging from a non-conducting string. Charge redistribution is induced by the presence of a nearby charged object, and in this case, net charge on the sphere is still zero. All we've done is redistributed the charge on the sphere. Now, if we touch the sphere with a grounded finger, that will remove the electrons on the sphere by contact, and the sphere is now left positively charged. The positively charged sphere is now attracted to the negative object. If possible, it will move toward the negative object and touch it. At that point, the electrons will move onto the sphere from the object. It will become negatively charged by contact, and then it will try to get away from the negatively charged object. Now, here's another way of doing this. We can take an initially uncharged, grounded conductor, and we will bring an object, a charged object, close to this conductor. In this case, the negative charges in the external object will drive the negative charges in the grounded conductor into the ground. And then we sever the ground, and then we move the external object away. At that point, we are left with a positively charged conductor that's isolated from the ground. Now, thunderstorms can occur just about anywhere, but thousands of them occur on the face of the earth every day. Charging by induction occurs in thunderstorms. A typical thunderstorm has positive charges at the top and negative charges at the bottom. The negatively charged bottoms of clouds induce a positive charge in the surface of the earth below. The negative charges on in the ground themselves actually retreat deeper into the earth, sort of like we did here. It's like this, okay? And that leaves positive charges clustering on the high points around like the tops of buildings and trees. As the charge in the cloud builds up, eventually the normally non-conducting air will break down, ionize, and turns into a conductor. That's a plasma. This is called a plasma streamer. The charge in the ground will then try to flow down the conducting plasma path in the air, and this is lightning. Most lightning is an electrical discharge between oppositely charged parts of the cloud. Some is between cloud and ground. That's the most dangerous kind, or between two different clouds. Or recently we discovered that lightning can also occur between cloud and air. The kind of lightning we are most familiar with is the cloud to ground. That's the electrical discharge between a cloud and the oppositely charged ground below, and that's the most dangerous kind, typically. You don't want to be between in this path in here. Now, have you ever been in a thunderstorm and it felt your hair standing on end? Well, that's a danger sign. That's a sign that you really shouldn't be there. Here's a picture of a woman, and her hair's all standing on end. She probably felt that hair standing on end feeling. This person is in extreme danger. If you look very carefully, there's a faint yellow plasma streamer. that is connected, running from the corner of her head up into the clouds. Now, this is what's really going on here. This is the unseen physics of the system. Here's the cloud bottom that's negatively charged. Here she's standing on the ground. The negatively charged cloud bottom is driving electrons out of her deeper into the ground. So she's becoming positively charged. And then the air starts to ionize and break down because any non-conductor under the wrong conditions, and this is definitely the wrong conditions, can become a conductor. So the air is becoming a conductor. And what's what they call a plasma stream or upward streamer starts to flow. Now, this is what will happen next, unless she got really lucky. This didn't happen to her. If you look very carefully, here's a tree in the process of getting hit by a lightning bolt. There was a plasma streamer up here on the top of the tree here that eventually caused this path to form, conducting path to form, and the lightning bolt followed the conducting path. And that's what this is. Now, if you look really carefully, you see a failed plasma streamer, one that didn't make the connection, reaching up toward the cloud. Now, where should this person, now the tree obviously can't move, where should this person go to avoid this? You don't want this. Get inside a sturdy building, which has electrical wiring and plumbing. Or a metal car, not a convertible or a golf cart. You want something with a metal body, preferably not a convertible, and no golf cart. Additional lightning safety. Stay away from high places, trees, metal poles, fences, and water. When thunder roars, get indoors. Get inside a vehicle, a metal top or body only. Wired building. The plumbing and electrical wiring will act as shielding. So is the metal on the vehicle. We'll explain later in the course why this is. Don't touch plumbing or wiring or things connected to them. Stay out of the shower and off the landline phone. Cell phones are okay as long as they're not plugged in. So don't be touching anything that's plugged in. If caught outside, do not lie down on the ground. A nearby stray can travel through the ground. You want to go inside and get as low as possible. We often put lightning rods on top of buildings. If I remember correctly, they were invented by Benjamin Franklin. So if a lightning rod is placed above a building, okay, and connected up to the top so its points stick up higher than the building, and they connect it to the ground, the sharp point of the rod will collect electrons from the air. The charges are attracted to sharp points. This prevents a buildup of positive charge by induction. The primary purpose of a lightning rod is to prevent the lightning discharge from occurring in the first place. The chiller bleeds it off. But if lightning does strike, it may be attracted to the lightning rod and short circuit to the ground, sparing the building. So it sort of acts like a shield for the building. It goes down the rod and down into the ground wire to the ground rather than going through the building. And you don't want lightning going through a building. Charging versus charge polarization. These two terms sound alike. Charging. Objects are electrically charged in three ways. Friction. Electrons are transferred by rubbing friction from one object to another. Contact. Electrons are transferred from one object to another by direct contact without rubbing. Induction. Electrons are caused to gather or disperse by the presence of a nearby charge without physical contact. Charge polarization. Charge polarization is the realignment or separation of charge rather than the wholesale migration of charge. This is charge polarization, in which the surface near the charged object becomes oppositely charged. Now, all checkpoints should be done before you look at them in the video or before you come to class. Do them in your notebook and then check yourself with them. That's why they're called checkpoints. Now, we have two metal spheres. Obviously, they're good conductors, and both are initially neutral and touching. We bring a charged object near them. Then we remove the charged object, and the spheres are separated. What happens? Okay, what's going to happen here is when the charged object is brought near, this one is going to become negative, and this one's going to become positive. But then we remove the charged object. These are conductors. The electrons are going to redistribute themselves over the two conductors, and then we separate them. So nothing's going to happen. So in other words, Q1 is 0 and Q2 is 0. They both wind up being 0. Now you have to, when you do this kind of problem, read them carefully and take them step by step. Sphere 1 and Sphere 2 are touching. Both are initially neutral. The charged object is brought near. The spheres are then separated. The charged object is then removed. So this is almost the same situation as we had before, but now we have changed the sequence of events. It's very important in this kind of problem to pay extreme attention to the sequence of events. So what has happened here is we brought the positive charge near these two spheres while they're touching. They're metal spheres. The electrons are free to move in the metal spheres. So the positive charge here attracts the negative charge to Sphere 1 and ends up driving all the negative charge out of Sphere 2, or most of the negative charge out of Sphere 2, leaving positive charge on Sphere 2. Then we separate the two spheres, and pull the external charge away. At this point, we're left with sphere 1 is negatively charged, sphere 2 is positive charged. So the correct answer to this is Q1 is negative and Q2 is positive. Okay, now based on the last experiment where two spheres were charged by induction, what can we conclude? Can we conclude that only positive charges move? Can we conclude that only the negative charges move? Can we conclude they both move? Or can't we draw any conclusion at all? We can draw no conclusion about which charges move. If we reverse the charges, the same results would occur. Thank you.